OK, let's get started. So today we're going to be continuing our venture into out-of-order processors and superscalars. And we're going to start talking about how to fix write after write dependencies and write after read dependencies in a processor pipeline. We're also going to talk a little bit about one of the questions we had last time about on a branch, what do you do to the reorder buffer, and how do you clean up the state in the reorder buffer? So let's start off. So a little bit about what we're doing today. We're going to talk about speculation in branches. As I said, we're going to review about that, and then answer the question we had last time about what happens to the reorder buffer when you have a speculative branch and what are good strategies there. Then we're going to talk about register renaming and how to break write after write and write after read dependencies. And then we're going to talk about memory disambiguation if we have time. And memory disambiguation is basically figuring out how to have loads and stores execute out of order relative to each other, and figuring out how to get the right data for a particular load after a store. And we call that memory disambiguation. OK, so let's start off by looking once again at our in-order pipeline, or I4 for short. And let's look at what happens on a branch. So here we have some code. Instruction 3 is a branch. Branch is to target T here. And it's executing along. And because everything is in order, we don't actually have to worry about any form of control hazard really happening here, or any form of really bad hazard happening here if we can just basically reach behind us and kill all of the instructions behind us. None of them will have committed any state at that point. So this is pretty nice. So we did have speculative instructions here, these 3 adds, and they started doing stuff, but they don't have a chance to get to the write back state of the pipe. So they don't even touch the physical register file. So we don't have to clean up physical register file. We don't have to clean up any of the state here. We do need to reset the scoreboard when we take a branch mispredict here, and the speculative state is wrong. But otherwise, everything is OK. OK, so life gets a little more complicated when we start to look at in-order in-order instruction fetch, in-order instruction issue, out-of-order execute and write back, and out-of-order commit. So here's our pipeline diagram. And what's interesting to see here is here we have our branch. Note that the sort of what is happening in the instructions moves around a little bit. But besides that, nothing much else is really changing here. We're still able to catch our speculative instructions before they write back. And what's key here is we're doing in-order issue. And it's because we do the in-order issue that the subsequent speculative instructions, while they are speculative, they're not going to run ahead and write back early, if you will. And what that would basically mean is we'd have for this add instruction, there's no W sitting here before this branch hits the branch resolution spot in the pipe. And let's say we resolve our branches in X0. And then, so this branch here can just redirect the front of the pipe. It can squash all the subsequent instructions and reset the scoreboard. So life is relatively easy. In-order issue, or excuse me, in-order fetch, in-order issue, out-of-order write back, in-order commit. Gets a little bit more complicated here. But what's nice here is we can prevent instructions from writing the physical register file for the same reason as the other pipe, because we did in-order issue. These subsequent speculative instructions cannot go execute any earlier. And we know that it's pretty quick to go actually issue or it's pretty quickly after we issue the branch instruction that we can resolve the target. So there's maybe a little bit of a shadow there. But if it's one cycle, nothing is going to be able to get to the write back stage of the pipe. Now, we do need to clean up the reorder buffer because this pipe starts to have a reorder buffer, so it's not just a scoreboard that we need to clean up, but we need to actually clean up the reorder buffer here. And we have an option. We can either remove from the reorder buffer immediately, or we can wait until these other instructions sort of get to the commit stage to remove from the reorder buffer. And this is the question we had last time, and I'll address that in 2 more slides in a little more detail. OK, so now we start to get to out-of-order issue processors. So here we have in-order fetch, out-of-order issue, out-of-order write-back, and out-of-order commit processor. And if you recall, this is the processor that we looked at last time, which we said could not have precise interrupts, because you can have things basically write early. Well, for that same reason, you can have instructions that write the register file, or write the physical register file early in a pipeline like this. Or actually, in this pipe, there's both architectural register file and the physical register file. It's all together. But if you take a look here, let's look at this add. This add writes the register file before the branch, which is dependent on the multiply, has been resolved. Uh-oh. Well, we just wrote the architectural register file. We wrote non-rollbackable state, if you will, or a state that is not able to be rolled back. And we actually committed the wrong state, and this speculative instruction was not supposed to have executed in correct program order. So this is the same problem that we see with imprecise exceptions showing up here. So one thing you could do is you could have a pipeline like this, and you can try to fix this by not having any form of control speculation. You can basically stall all these subsequent instructions here, these 3 adds, and actually potentially all the rest of these question mark instructions here until the branch has been resolved. But that's going to limit your performance. So there's a problem with this form of pipeline with out-of-order commit here, is that you have no way to sort of roll back any state. OK, so this takes us to our pinnacle pipeline that we had last time. In-order issue, or excuse me, in-order fetch, out-of-order issue, out-of-order execute and write back, and in-order commit. And let's take a look at this. There's sort of 2 competing questions here that we have to think about. First thing is, we see that this actually does a write right here before the branch is known. But conveniently, it's writing a different data structure. It's not writing our architectural state. It's writing our physical register file. And just like on a interrupt of some form, we can roll back the architectural register file into the physical register file. We can do that for a branch here also. So one of the interesting questions that comes up is, where do we resolve the branch? And when do we try to kill subsequent instructions? Do we try to do that right when the branch gets resolved? Oops. Or do we wait till the branch commits? OK, so this actually goes back to the question we had last time of how easy is it to go clean up the reorder buffer, and how easy is it to go clean up the physical register file. So let's take a look at this example here. Now, having said that, this is all doable. People have built pipelines where they actually do go clean up sort of all these in-flight instructions. But let's look at the complexity of that. So here we have, right when we know the branch gets resolved, we actually kill all of these instructions, and we redirect the front of the pipe to go fetch our target, our true target. Well, let's go look what's happening in the physical register file for this case. So in this case, for the physical register file, this mul has written the physical register file. That's a good value. We want to keep that mul. This add here has also written the physical register file. We don't want to keep that. Ugh. Life starts to get a lot more complicated here. In a pipeline like this, what we're really going to have to do is we're going to have to clean up speculative state in the physical register file, and we're going to have to do selective rollback. So instead of just taking the entire architectural register file and overwriting the physical register file on rollback, we're going to have to figure out which of these things were speculative, which of these things were not speculative. That's doable, but you probably need some extra structures to go do that over and above what we've already talked about in class. Or rather, you're going to have to track which physical registers need to be rolled back on a speculation mispredict. Something a little bit easier is just to wait to the commit stage. So if we wait to the commit stage, we can see here as we commit, well, we know that all of the previous instructions of this branch have committed now to the architectural register file. So we know the architectural register file is up to date relative to the branch. So we can, and these other speculative instructions may or may not have written in the physical register file. The physical register file is just completely out of date at this point. So what's nice here is we can copy the entire architectural register file to the physical register file and effectively roll back everything. OK, so this brings us to the question that we had during last class about the reorder buffer and what do you do with reorder buffer pointers in this branch misspeculation case. So the question really here is, well, do we have to wait for these instructions here to get to the end of the pipe, these speculative instructions to get all the way to the end of the pipe to go clean up the reorder buffer, or can we just adjust a pointer of the next instruction in the reorder buffer? And the answer, so I spent a bunch of time thinking about this, is we should just be able to adjust the pointer in the reorder buffer to say where the next location is and just fill that in with this target instruction here. And that will effectively clean out all of this state here. But where this gets tricky, that works great in this case. But as I said, if you go look at this other case here where you actually you're trying to preemptively sort of kill things, this is not going to work in this case. Because what's really going to happen is we have selective rollback we're going to have to perform here. And just changing the pointer in the reorder buffer is not enough to go do that. We're going to have to sort of individually clean up entries if we want to go do that. And that gets a lot more complicated. One other thing which we haven't talked about yet, and one motivation for why you may want to wait to actually clean up the reorder buffer until you want to wait till the speculative instructions reach the end of the commit stage of the pipe, if you will, to clean up the reorder buffer, is there's other structures, if you have a register renamer, which you're going to want to clean up in that same manner. So we're going to be talking about register renaming in this lecture. And what happens is if you sort of think about these in-flight speculative instructions, if you have more physical registers than architectural registers, it's possible that if you have to abort these instructions, these speculative instructions, you have other structures like a free list of physical registers, which you have to deallocate somehow. And you can sort of do like a bulk deallocate, but it's a convenient place to sort of deallocate when it tries to commit. So let's look at that in a minute. But that's basically what I want to get across is, yes, you can just adjust the pointer for the simple case. Trying to do something more aggressive gets quite a bit harder because you have to speculatively roll back the physical register file in addition to the reorder buffer. Well, the reorder buffer, you can just adjust the pointer, but the physical register file, you can't just do that with. And if you wait to the end of the pipe, you can deallocate physical registers a little bit easier.